Planes fly underneath this bridge, not because it crosses an airstrip, not because it sits near an airport, because it hangs 500 to 65 meters above the river below, higher than the Eiffel Tower stands tall, higher than the clouds that drift through the Beipan River Gorge on a normal morning in Guizhou Province. Driving across it feels like floating through nothing. Look left, look right, and the earth has simply disappeared. The gorge drops away on both sides, and the only thing between you and the valley floor is 10,000 tons of steel suspended on cables that engineers once said could never be anchored here at all. Before this bridge existed, crossing this gorge meant 5 hours of mountain roads, switchbacks carved into cliff faces, descending to the valley floor and climbing back up the other side, in a province where that journey had to be made by everyone who had any reason to move between the communities on opposite sides. Guizhou Province has always been one of the most isolated places in China. Millions of people lived completely cut off from the economic corridors that connected the rest of the country. No highways, no fast routes, no expressway at all until the year 2000. The mountains that made Guizhou beautiful made it a trap for the people who lived inside it. China's government made a decision: connect Guizhou no matter the cost. The investment in infrastructure that followed transformed the province over 2 decades, but every highway plan that tried to cross the Beipan River Gorge hit the same obstacle. The gorge was too wide, too deep, too exposed to wind, and too geologically complicated for any conventional bridge design to work. Every traditional approach failed at the drawing board. For 13 years, the gorge stopped every highway plan that came near it. Engineers studied it, proposed solutions, rejected them, and went back to the drawing board. The gorge was the problem that could not be solved. 2 years of dedicated study of this specific gorge before a single design was approved. 2 years of measuring wind, mapping geology, drilling core samples from the cliff faces, and modeling every conceivable structural approach against the real conditions of the site. The wind data collected during that study period was, by the account of every engineer who reviewed it, absolutely terrifying. Gusts reached 140 kilometers per hour in the gorge, not occasionally. Regularly, a structure hanging 565 meters above the river in that wind environment had to be designed not just to survive the forces, but to be buildable in them by workers who would be exposed on cliff faces and open steel platforms with nothing below them for the full height of the drop. In 2011, one engineer proposed the design that finally made the crossing possible: a cable-stayed bridge, but with a configuration that had never been used at this altitude or in this terrain. The towers would not stand on flat ground beside a river. They would grow from ledges cut directly into the cliff faces on opposite sides of the gorge, anchored into the solid rock of the canyon walls, rising to a height that brought their tops level with the gorge rim itself. The cables running from those towers to the deck would carry the full load of the bridge down through the towers and directly into bedrock. The cliff was not the obstacle. The cliff was the foundation. Construction officially began in November 2011. The challenges started before the first piece of equipment reached the site. There were no roads to the cliff faces, no cranes that could operate at these angles and in this wind, no way to move materials across a 720-meter gap between 2 vertical rock walls. The site was so extreme that the normal assumptions of construction logistics simply did not apply. The first task was not foundation drilling. It was building the infrastructure needed to build the infrastructure. A cross-gorge cable system was designed and installed specifically to move equipment, materials, and workers across the gap before any permanent structure existed to carry them. A temporary aerial ropeway spanning the full width of the gorge in 140 km/h wind conditions, operated by workers who could not afford a single mechanical failure at that height. Before foundation work could begin, roads had to be carved into the cliff faces. 200 controlled explosions cleared the cliff face on each side, creating the ledges and platforms that workers and machinery needed to function. Not 200 blasts fired in sequence and left. After every single explosion, geologists inspected every millimeter of the remaining rock face for new fractures, new weaknesses, new instabilities introduced by the detonation. 200 blasts, 200 inspections. The cliff had to be known completely before anyone put weight on it. Every anchor point point for the tower foundations was drilled by hand into solid bedrock. No machines could fit in the working space available on those cliff ledges. Workers operating handheld drilling equipment suspended above a 565-meter drop, boring holes 15 meters deep into the rock face at angles calculated to transfer load into the strongest available geology. No exceptions to the 15-meter depth requirement. No shortcuts taken because the position was difficult or the conditions were brutal. 8 months of this work before both foundation pits were declared ready for concrete. The concrete pour for each tower foundation required 15,000 cubic meters, placed continuously without stopping. The same logic that governed the Three Gorges Dam applied here at smaller scale. Stop the pour midway, and the cold joint created at the interruption becomes a permanent weakness in the foundation of a structure, carrying 10,000 tons of steel in a wind environment that would exploit any weakness it could find. 15,000 cubic meters per foundation, poured continuously in a working space cut into a cliff face 565 meters above a river, with workers operating in wind that could throw a person off the ledge without warning. Every worker platform was fully enclosed. The wind at that height does not give warnings. The towers grew from the cliff edges using a self-climbing concrete formwork system that advanced 4 meters every single day. Each meter of height required a laser check for vertical alignment. 1 degree of deviation off true vertical, and the tower would have to be demolished and rebuilt. The wind that made the site dangerous also made the precision requirement harder to meet. Concrete forms that are perfectly level on a calm day shift in high winds. The measurement crews worked continuously, checking and rechecking alignment at every stage of the climb. Tower 1 reached 100 meters in just 62 days. While it grew, the team on the opposite cliff face was already 40 meters ahead of it. 2 independent construction operations, separated by 720 meters of open air, racing the same timeline with no ability to directly coordinate except by radio. Winter arrived in 2012. Temperatures dropped below zero. Work never stopped. Concrete cannot be poured in freezing temperatures without intervention because ice, forming in the mix, destroys the chemical bonding that gives concrete its strength. Heating systems kept the pour temperatures within specification. The towers kept climbing. Inside each tower, a system of pre-stressed cables runs through the concrete, holding it under permanent compression. Concrete is enormously strong in compression and relatively weak in tension. The pre-stressed cables ensure that the forces the tower experiences in operation never put the concrete into tension. Every computer simulation run during the design phase showed the same result. This design, in this configuration, could handle anything the Baypan River Gorge could produce. After 18 months of construction in conditions that would have shut down most sites, both towers stood complete. 392 meters of concrete growing from cliff edges. Each tower top holds 56 cable anchor points, each one engineered to handle 4,000 tons of pulling force. Then the gorge was still empty. The cable installation phase was the most technically complex part of the entire project, and it began with a helicopter. The first wire across the 720-meter gap was a thin pilot cable run by a helicopter pilot hovering in 80-kilometer-per-hour crosswinds, while workers on each cliff face attached the wire to the anchor points. The flying skill required for that operation was extraordinary. Hold a hover in gusty mountain crosswinds with enough precision to thread a cable attachment in a specific location, while the downdraft off the cliff walls created unpredictable turbulence. Get it wrong, and the cable falls. Get it right, and the entire installation sequence can begin. From that first wire, the full cable installation built outward, 56 cables per tower, each cable containing 109 individual high-tensile steel wires twisted together under precise tension. Every new cable installed changed the tension in every cable already in place. The system behaved like a musical instrument being tuned. Adjust one string, and every other string changes pitch. Each cable had to be tensioned to within 1% of its target load, checked against every other cable in the system, adjusted if any interaction had shifted it outside tolerance, and checked again. The process required continuous measurement and continuous correction across all 112 cables simultaneously, 4 months to complete the installation. When the final cable clicked into its anchor point, engineers who had spent years on this project were hugging each other and crying. Then the cables started singing. The wind flowing through the gorge found the cable frequencies and began driving resonant vibrations in the steel. Uncontrolled resonance can fatigue a steel cable to failure. The failure of a single cable in a cable-stayed bridge at this scale begins a load redistribution that the remaining cables may not survive. The problem had to be solved before deck installation began. The solution was viscous dampers, one fitted to every single cable at its housing point, engineered to absorb the energy of the vibration without constraining the cable's structural movement under load. Before and after the damper installation, same wind, same cables, the vibration gone. The problem found during installation became a safety system that would protect the bridge for its entire operational life. The deck was built from both towers outward simultaneously. No other sequence was possible. Build from one side only, and the load imbalance would pull the tower out of vertical. Every deck section was prefabricated off-site and brought to the gorge by crane, lifted into position 565 meters above the river, bolted and welded in place by workers who could look straight down through the gaps in the growing structure and see nothing but the Bay Pan River at the bottom. Every bolt torqued to precise specification. Every weld made at full height with a thin safety net as the only barrier between the welder and the valley floor. Some days, the wind hit 120 kilometers per hour. Work stopped for nothing. As the two arms extended toward each other from opposite sides, the stress calculations for the entire structure had to be rerun from scratch after every new section was added. Inside the deck is a sealed steel box. Inspectors crawled through it at every stage, checking every weld from the inside in conditions of complete confinement, because a weld failure inside a hollow steel box deck at this scale and altitude is not something that can be discovered after the bridge opens. When the two arms were close enough to measure precisely against each other, engineers found that the two deck ends were 3 centimeters out of alignment. 3 centimeters across, a structure 1,341 meters long, built in sections from 2 different cliff faces, separated by 720 meters of open air, is a result that speaks to the precision of everything that came before it. By adjusting the tension in 12 specific cables, engineers moved the entire deck into alignment without touching a single physical component of the structure itself. After 18 hours of micro-adjustments, the two ends were within 2 millimeters of each other. The closing piece weighed 120 tons. It had to drop into a 120-ton shaped gap with the precision that the alignment operation had created. 200 workers synchronized by radio, all moving at exactly the same moment. When it landed, the two sides of the Bay Pan River Gorge were connected for the first time in the history of the region. The workers started calling it the day the gorge disappeared forever. 1,341 meters of steel deck completed in 10 months. Before the road surface could go down, engineers laid a 20-centimeter reinforced concrete base across the full deck length. Paving took 6 days of continuous work, 24 hours a day without stopping, because a cold joint in the road surface of a bridge at this altitude creates exactly the kind of differential settlement that would destroy the surface over time. 600 sensors are embedded throughout the structure. The bridge reports its own structural health in real time to a control room staffed by engineers who monitor it the way a hospital monitors a patient's vital signs. The expansion joints in the deck allow 60 centimeters of movement. In Guizhou's climate, the bridge steel expands and contracts by half a meter every year as temperatures change across seasons. The structure breathes. The joints let it breathe without cracking. The load test brought 80 trucks to maximum gross weight onto the bridge simultaneously. The deck deflected 45 millimeters exactly, precisely matching the computer model prediction. The model that had been run thousands of times in the design phase was validated in a single day against the real structure under real load. The wind data matched. The deflection matched. Years of calculation confirmed in one afternoon of testing. The final inspection report was 4,000 pages long. Every calculation checked and verified twice. 3,500 workers had built this bridge over 5 years. Before it opened to the public, every single one of them walked across it. December 29th, 2016. The ribbon was cut at 10 o'clock in the morning. The first official convoy crossed in 4 minutes. The journey that had taken 5 hours of mountain roads took 4 minutes on steel and cable. Elderly villagers who had walked mountain paths their entire lives stood at the roadside and cried. On the first day, more than 3,000 vehicles crossed the world's highest bridge. Within 24 hours, images of it had been seen by 500 million people online. One business owner reported that his delivery time had been cut by 97%. That is not an improvement. That is a transformation of what economic life means for the people of Guizhou province. Guinness World Records confirmed it officially. World's highest bridge, 565 meters above the Beipan River, higher than the Eiffel Tower, higher than the clouds. They said nothing could be built here. Then they built the highest bridge on Earth anyway. That is what humans do at their best. Like, share, and subscribe for more.